Welcome to today's webinar. The topic today is stability in steel construction, overview of 3 key design methods. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, customer projects, and so on. I will be the moderator today, and I will also present the webinar. I will be supported by my colleague Sonja von Bloh. She is responsible for the development of the add-ons aluminium design, section, steel design, and she works also in the customer support team. Okay, at least for the attendees who participate the first time, I say something how you can ask questions. First, I switch off my webcam that you can see the full screen. If you have a question, just press the button with the question mark, then enter your question in that field. Press send, and Sonja will receive your question and she will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. To the agenda today, first point is theoretical basics. Now, it's only a small chapter in this webinar. It should be more a practical webinar. I've got only 3 slides. Then I start with the first example. I use the equivalent member method, then the general method, and in the third example, the torsional warping analysis, the second order analysis with 7 degrees of freedom. Okay, let's start with this overview table where the stability analysis methods are compared. And you can see the limits of the different methods in the table. We go through this table line by line. First line, equivalent member design according to 6.3.1, according to Eurocode 3. This is for uniform members in compression. You can see I sections are valid. Hollow sections, and also other sections are valid, but only compression. And then the different designs, flexural buckling, torsional buckling, and lateral torsional buckling, are done. And examples for these methods would be hinged columns or compression members. Then the second line, equivalent member design according to 6.3.2. Uniform members in bending, about the principal axis, and lateral torsional buckling due to bending will be done. And it means this method is for pure bending beams. Then the third line, equivalent member design according to 6.3.3. Uniform members in bending and axial compression. This method is only valid for I sections and hollow sections, or that means all double symmetric sections are performed. And you can see normal forces and moments about the strong and weak axis are possible. And then the different designs, flexible buckling, torsional buckling, and lateral torsional buckling will be done. Okay. Then the fourth line general method according to 634. This method is valid for uniform and non-uniform members, and single symmetric sections with compression and bending about the principal axis. Then the fifth line, designed according to second order analysis with 7 degrees of freedom. Now you can see all is possible, uniform and non-uniform members, all cross-sections, all internal forces, but imperfections must be applied and the second order analysis must be done, and the 7th degree of freedom must be considered. That means that we have to activate the warping torsion analysis. Now we will do that later in example. And with the examples, I will compare these 3 methods. Equivalent member design according to 633, general method, and the design according to second order analysis with 7 degrees of freedom. Let's start in the program with this example. In the first step, I activate the steer design. I go left above to the base data. Then I activate add-on steer design. And now we would like to design according to Eurocode 3 and the European Annex. Okay. That's the example. You can see it is different, these constructions in longitudinal direction with bracings, and in this directions with the frames. That's the loading. Same loading for all frames. Because we would like to apply later a horizontal load on this frame to compare the different methods. Then we only create one load case. Doesn't matter. Today the combinatorics doesn't matter. The focus is on other things in this webinar. So I show you the imperfections that are applied. First, this initial strain, according to Eurocode 3, height of the structure, and so on. And this value is calculated automatically for the initial strain. Then I applied also this member imperfections in initial bow and criterion. It will only be applied if this condition is fulfilled. That's not the case in our example, but I would like to show you how to apply such initial bow and criterion. Okay. Then we go to the load case and combinations. So you go to the measure index, then the load case. This is only one load case, one load combination. The imperfection is considered, and this is the design situation, and the steer design is activated. And in this webinar, we only focus on the ultimate limit state design. So, okay. Then I created previously a member set for this horizontal beam, and I activated design properties. So in the equivalent member method, application for straight sets of members, and the low thrust inclination is not considered here. So then we go back to the set of members with a double click. Yeah, and we would like to use the equivalent member method. That's why we check here, or we have to create a new ultimate configuration. I know that's not the right table, sorry. Design types. We need to create effective lengths for the equivalent member method for stability design. Now we would like to consider flexural buckling in both axes, then the torsional buckling and the lateral torsional buckling. So then we've got intermediate nodes. With this button, I can import the intermediate nodes. Okay. So, and we would like to consider or check this placement in Y direction. Okay, we can see it better here when I click this button. Okay. Fork support and horizontal support in the intermediate nodes. Okay, that's all. And now we turn to the ultimate configuration. Let's check this. I would like to perform the stability analysis. And we can uncheck this box, the equivalent member method and the general method already account for gamma 1 in the formulas. Okay, and we leave all the default parameters now from the standard. Okay, then the columns. I select both colors and double click on it. Both columns are selected. Then I check the design properties. Then design types. And we have to create new effective lengths. All the stability design will be done. And this is also okay. I use this settings for the columns. Buckling length is equal to the member length. And we also, we applied imperfections and we calculate according to second order theory. That's why this is valid. Okay. And I can also display it here in the model if I defined all correctly. Types on the navigator display. types for steel design, member effective lengths. Now you can see all the supports and effective lengths here. Okay, then we turn to the steel design. Now, ultimate limit state design, objects to design. Yeah, I would like to design the member set, the horizontal beam, and the two columns. Now we would like to design only the first frame in this webinar. Okay, then we can start the calculation. Okay, the calculation is done. You can see the design checks. We are about 70% here and 55% for the columns. So let's go to one design, for example, this one. You can see the equations from the standard and also the equations that were done here, right? Okay. Now, and the design ratio. And you can see also the eigenform here for the horizontal beam. When you click on this design check. Okay, that was the equivalent member design. Then we turn to the next model and the next design method, the general method. So that's the same structure, but in that case, I created a member set. This one. It contains the columns and also the horizontal beam. Then design types. This time I have to create boundary conditions because I would like to use the general method for the stability design. So that's correct. Null supports. I check or press this button again to import the intermediate nodes. Oh. Then I support, or we would like to support, the frame in this direction. You can see it better here when I click the button. So horizontal support, and we would like to apply a fork support on the column base. Yeah, and that's at the moment not correct because the program uses this axis, and it would be correct for this node, but we have to rotate the support here. So I select both column bases with the control key and I rotate the support. And now we've got the fork support on the bottom of the colors. Okay, that's correct now. We can leave the dialog. Okay. And you can see the complete frame is here, and you can see the condition, support conditions. Okay, we can again take a look at one here. Number effective lengths. This time boundary conditions. You can see if all is applied correctly. Again, here, the global model. So then objects to design, again, only the member set. It includes in this time also the columns. That's why we only need to check the member set here. So start calculation. It's done. Okay, and now we can see the design ratios. About 60% for the horizontal beam and about 70% for the columns. Let's compare both methods. So then window horizontally. Don't display the table. Window horizontally. Take a look in minus y direction here and also minus y direction here. Now you can see those are different methods with different conditions. The results are nearly the same, but not exactly the same. Those are different methods. For the equivalent member method, we applied fork support here, and for this method, fork support on the bottom of the columns. And it's not the reality in both methods, but near to the reality. And I think the result is nearly the same, but it must, or it's not necessary, or you can expect that you get exactly the same values or design ratios. So then I apply a horizontal load for both models. For the equivalent member method first. So load case 1 minus 1 in y direction. Okay. Only for the frame. Okay. So we can start the calculation again. Steel design. Okay, we get nearly the same results. The design ratio is a little bit increased because of the low horizontal load. But what I would like to show is what happened with the general method. We apply the same method, same load. Minus 1 in y direction. Okay. Start the steel design. So, and now we get the error message that the general method is not applicable. Let's turn back to the PowerPoint slide. The reason is for the general method, the moment about the weak axis is not possible. Yes, for the equivalent member method, but not for the general method. So that's the limit. We turn back to the program. I close both of ones. And I group in another model. I group in it in the Dlubal center. That's on the other screen. Just wait for a moment. So now a similar model, but now with tapered frames. All the loads and all the imperfections are the same. Yeah. As for the previous models. And now we would like to use the general method again. That's why I open or I select the member set for the complete frame with a double click. Design properties, design type, and we need to set the same conditions. I go quickly through it. Okay. I have to rotate the supports on column basis again. 90 degrees. Okay. Okay. So, and now we can run the steel design. Sorry, I have to cancel it. We only want to design the member set. Okay. Okay. We got design ratios about 60%. Can also see the eigenforce, but if it's displayed like this way, you have to go in the navigator results, the formations, members, section colored. Yeah, and now you can see the eigenform. So, okay. Then we apply the horizontal load also for this model. And Y direction. Okay, the general method is not applicable again. Let's turn back to our table. In the first step, we had a non-uniform member. That's okay. But now in the second step, we applied a horizontal load and we got a bending moment about the weak axis. And that's why this method is not valid. So let's turn back to RFEM. modifier, save as. So I saved it as warping torsion analysis, because that's the next step that we would like to apply the warping torsion analysis. So at first I activate in the base data left above the add-ons structure stability and the torsional warping, with the consideration of the 7th degree of freedom in the global model. Okay. So then I delete this set of member with the that contains the complete frame. We only create a set of member toward the horizontal beam now. Right click. I selected all the members, then right click members, create member set. Okay. So, and I need to activate the design properties. But we don't create any boundary conditions or effective lengths here. We would like to do the design with the application of the imperfections in the weak axis and so on, and use the second order analysis and the consideration of the 7th degree of freedom. So we start with stability design. To do that, I turn to the load case and combinations with right click. Load combinations. We have got only one load combinations, and I activate the structure stability analysis with first 10 eigenvalues and S-not calculation. Okay. We have to turn to the member set, and we have to check the discontinuous torsional warping. Okay, and run this calculation for the combination again. You can see that this is the stability design. Static analysis and stability analysis. So then we check the stability analysis here. Now, so you can see the different eigen shapes. We would like to design only this frame. The eigen shapes are quite similar. I select only this frame for a better overview. Okay, you can see it's quite the same eigen shape. So then I turn to the panel that I can see the panel. Increase the value a little bit. So let's take a look at different mode shapes. This one, then the second one. take a look at the columns and the horizontal beam, where different mode shapes are buckling in this direction, now in this direction and this directions, and you can see the shape for the horizontal beam. We would like to apply imperfections in the horizontal direction. That's why I take a look at the mode shapes UI. Okay. So, and the conclusion is we have to apply different imperfections. In the first step, I deactivate the stability design. Okay. So now we create a new imperfection case. So then imp y command and case 1. Okay. Case 1, and I apply the imperfection. So initial bow, then manually relative in global axis system, y direction. Yeah, and what I have to enter here, I will show that on the table, on the next table. Pre-camber, those are the limits from the standard. The key value is 0.5. We have got welded sections, H to B larger than 2. That's why we have got buckling curve D. And in this table, you see for the buckling curve D and the elastic design, 1 divided by 150. The elastic design will be done in the warping torsion analysis. That's why we need to use this value, but you can see the key value is 0.5. That's why we apply 1 divided by 300. So let's turn back to the program. 300. Okay. And on all the members here. Okay. So, and now I copy the imperfection case 3 times with that button here. Okay, and I rename one it's 2, case 3, and case 4. Okay, and now I change the different directions. So for case 2, I change this direction. With the control key, I can select more than one. So this one, double click, and I change the direction in reverse y direction. Okay. So now we have this imperfection, then case 3, this one, this one, and this one. Double click, and now the same workflow. No, that was not correct. This one should be remain in this direction. Okay. Case 3, then case 4. I change only the directions, imperfections on the columns. Okay. Now, and if you are unsure, you can create more imperfections, more cases. Let's go through all the cases. We would like to design or do the design only for this cases or for this imperfections. So in the next step, I open the load cases and combinations dialog with a right click. Load combinations. I copy that load combination 4 times. With the button, the bottom. So then I apply imperfection case 1 here. Case 2 for this one. Case 3 for this one. And case port. Okay. So then, now this is done. Now we can go through the different load combinations with the imperfections. On also show the loads. So then, okay. Now we would like to do the steel design. I go to steel design and the ultimate configuration. We can open this also when we select the members and the member set, but we would like to do it for all. That's why I select here, click on it. Yeah. We don't check this one, perform stability analysis. We want to perform the stability design using the cross-sectional design. So, yes, and we check this one, stability analysis with second order internal forces. Okay. Then skill design for the member set and also for the 2 columns. Okay, and I run the design. Okay, all designs are fulfilled. We can see we have tabled beam, we have loads in all directions. For this method, all is possible. But it's a little bit more difficult to apply the imperfections. That is what you can see. So this is the formula from the standard. It's also the highest design check ratio. And that's the formula. And now you can see it's an elastic design. And we've got also the possibility to do a plastic design. So at first I save the file 2 times. File save as. Okay, torsion analysis finished. Later you can download the models from our website. Save and file save as. Finish. That's great. Save. Let's turn back to the ultimate configuration default. I click on it. So, and we have got the possibility to perform an advanced plastic design. Let's check that. And you can see this new dialog here. If plastic design is required, the partial internal force method can be used. But please combine it only with warping torsion analysis, as no stability design is performed. The stability is verified for the entire system using second order theory, warping torsion analysis, and imperfections, what we applied previously. So then, the plastic design according to Eurocode 3 is only valid for cross-section classes 1 and 2. And the partial internal forces method with redistribution is only for 2 and 3 sheet cross-sections. For this method, there's also a knowledge base article available. I would like to show that on our website. Under support, you can find the knowledge base. And if you, for example, search for plastic, you can find this article, plastic cross-section checks using partial internal forces method. If you can read this article if you want. So we are back in RFEM. Okay. So and now we would like to do a plastic design. That's why we need to increase the imperfections. Let's turn back to the PowerPoint slides. You can see that's for the elastic design. And for the plastic design, 1 divided by 100 multiplied with p-value 0.5 means 1 divided by 200 is that what we need to apply. So let's select all. I double click on the imperfections 200. Okay. For all cases. Now the direction remains. Oh, I didn't select this one. That was my fault. Sorry. Was it correct for the first case? Yes. It's also correct. So then, case 200. Okay. So in the last case, okay, so let's run the calculation. Okay, and you can see, where are quite small, design check ratios. Let's compare it. We open the other file again, copy torsion analysis. Okay, window tab horizontally. Let's see the I hope you can see all without notes. So you can see for the horizontal beam with the plastic design, we have smaller design check ratios. But for the color on this node here, or on this place, you have got a higher design ratio. Now, why? The reason is that is a cross-section class 3 here, and the plastic design can't be done. But we have got higher imperfections, and that's why we get a higher design ratio on this place here. But you can see lower design check ratios here. Let's check this value. So that's the design check. I double click on it. So section classification, and you can see cross-section class 3. And that's why the partial internal force method can't be applied. Only elastic design is valid. Okay. Those are the 3 models and the 3 methods that I compared. I hope you got a good overview. In my opinion, the equivalent member method and the general method are simpler to apply, but you have different limits, restrictions. The design according to second order analysis with certain degrees of freedom allows all components, all cross sections, all loadings, but the application of the imperfections are a little bit more complex, I think. At the end, I would like to give you a hint to our online courses before I have a small surprise for you. There is the RFEM 6 masterclass course. It's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design. The Eurocode 3 course for the steel design. Eurocode 5 for the timber design and Eurocode 8 for the earthquake design. For more information, just scan the QR codes in the middle here or click the links at the button on the bottom. Okay, that's the small surprise. Today and tomorrow you can get the Eurocode free course for a reduced price, not 299 euros, but only 96 euros. Yeah, just scan the QR code and you can start your course. It's the course, it's 4 hours long. It has different chapters. You can stop the course and continue anytime. It's there's also no end date. It's valid forever because it's very cheap, I think. Okay, that should be all for today. I hope I could give you a good overview over the 3 design methods for the steel design. Also the additional plastic design method for the warping torsional analysis. Just use also the overview table in the slides. You can download the slides from the same page where you can find the recording and the models that I presented today. Today or on the next days, you will get an email with a link to the page where you can find all. And just use the reduced price for the Eurocode free course. I thank you for your attention. Thanks to Sonja for your help by answering the questions. I hope we meet each other in a future webinar. I wish you a nice rest of the day. Bye-bye.